Okay, so let us now start this next section, characteristic roots. Now, throughout the rest of this chapter, our focus will mainly be on linear operators on finite dimensional vector spaces. So, we are going to assume from now on that V is a finite dimensional vector space over some field. We will denote a finite dimensional vector space over a field F. So, this finite dimensionality we are not going to mention explicitly anymore, okay, unless we have some compelling reason to do that. Alright, now we know that the algebra A of V has a unit element 1, which is actually nothing but the identity operator on V, and that is the operator which does not change any vector. You put any V from V, it's going to give you that V back. Finally, for any scalar lambda and any operator T on V, we write the operator lambda 1 minus T simply as lambda minus T. I mean, without this new notation, this by itself will be meaningless because we cannot subtract an operator from a scalar. But when you see this, it's going to mean this actually. Alright, so with all these notations and convention everything, let us start the section with the definition of characteristic roots. Let T be an operator on V. We say that the scalar lambda, of course it's going to come from the underlying field F, is a characteristic root, also called an eigenvalue of T if lambda minus T, that is this operator, is singular. We know that this operator is of course ultimately an element in our algebra. So it is either regular or singular. If it is singular, then we will call this scalar lambda a characteristic root of T. It's also called an eigenvalue, but we are not going to use this term in this text. Now, because it's a little cumbersome to keep writing characteristic root, I will just write CH full stop root, okay, CH root. Alright, so let us now see what this thing has to do with vectors in V, somehow can we link lambda being a characteristic root of T to the vectors in our space. So there we have this theorem. Let T be an element in A of V, then lambda in F is a characteristic root of T if and only if there exists a non-zero vector V in V such that if you apply T on V, you are going to get lambda V. And in fact, this condition itself is sometimes taken as the definition of a characteristic root. And the vector V in this context, which is not necessarily unique, is called a characteristic vector or eigenvector. That term, however, is, it will come afterwards, not now. So let us now see the proof of this. Our definition of characteristic root or eigenvalue, however, is via singularity of a linear operator. But of course, now we will show that it's equivalent to the availability of such a vector. Proof. Let lambda be a characteristic root of T. Then by definition, lambda minus T is singular, and at this point we are going to recall one result from the previous section. We know that singular operators send not just the zero vector to the zero vector, but something else also. Any singular operator sends at least one non-zero vector to the zero vector, and that result is theorem 613. By theorem 613, there exists a non-zero vector in V such that if you apply our operator, singular operator on that vector, then you are going to get 0. That is the nature of singular operators. And from this, if you do the calculation, you are going to get this equation, of course. Okay, so now we see the converse. Conversely, let Vt be equal to lambda V for some V not equal to 0 in V. Then we have this, but then again by theorem 613, which is an if and only if statement, lambda minus T cannot be regular. And you can also see why that is the case. If lambda minus T is regular, then it has its inverse. So applying the inverse to this vector and to this vector, that is going to give us the same thing. On this side we will have v, on this side of course we will have 0, getting v equal to 0, but v is not equal to 0. So that is why lambda minus t is not regular, it is singular. By theorem 613 again, lambda minus t is singular, and so lambda is a characteristic root of t. And that completes the proof. Alright. Now there is another result after this, which involves polynomials over the underlying field and characteristic roots of linear operators. The result by itself is not that important, so it is going to be called a lemma, but it has a consequence. Okay, we are going to see that also, which is a very easy consequence of this lemma, but that is much more important than the statement of the lemma. So that will be a theorem in spite of being an easy consequence, because a theorem is more important than a lemma or proposition. Let T be in A of V and lambda in F be a characteristic root of T if Qx is a polynomial over F, then Q of lambda is a characteristic root of Q of T. Okay, this is the claim. Let us now see the proof. Let us write the expression for this polynomial. Let Qx be alpha naught x to the power m plus alpha 1 x to the power m minus 1 and so on, alpha m minus 1 x plus alpha n, which means that these alpha i's are of course coming from F. Alright. Now we will not use the definition of characteristic root itself, but the previous theorem which links these things to that non-zero vector V. Because it is given that lambda is a characteristic root of T, so that V exists. By theorem 621, Vt is equal to lambda V for some non-zero V in our space. Now what we are going to see, we will see the effects of higher powers of T on V. Say, let us first see what is Vt square. Note that Vt square, we are going to need these things because we have this polynomial. Okay, you can understand if you evaluate Qt, you are going to get powers of t here, and that if you apply on v, you need to know what this kind of things are actually. Vt square is nothing but Vt t, and Vt is lambda v t. Because t is linear, this is lambda times Vt, and this is again lambda v, and these two scalars of course come together by one of the vector space axioms, and you get lambda square v. So when you have t square, you are getting lambda square, and if you continue this calculation by next calculating Vt cube, I mean you can almost see that you are going to get lambda cube v. Similarly, because there you are going to apply t 3 times instead of 2 times. And so on. Okay, now the next thing we want to see is this VQT. What happens if we apply QT on V? Let us first write what QT is from there. Alpha naught t to the power m plus alpha 1 t to the power m minus 1 and so on, plus alpha m minus 1 t plus alpha m. If you want, you can write, you can keep it alpha as alpha m. However, it's better to write 1 because otherwise some confusion may arise. We may forget that this is not simply a scalar, but along with that we have the unit element of our algebra also. Okay. Now in the next step, we are of course going to use the definition of all the operations. That means the 3 operations we have in our algebra: addition, multiplication and scalar multiplication. By the definitions of those things, this is equal to this plus alpha 1 v t to the power m minus 1 and so on v t plus alpha m v 1. Okay, and now you use these observations. Whatever exponent you have here, that exponent you are going to have also for lambda. That similar power. So that means here you are going to get this, next this, plus alpha m minus 1 lambda v plus alpha m 1. Of course, it's the identity operator, so on v it has no effect. It's going to give you v back. Now I can of course write at once what I finally want to write, but let's go systematically. Okay, using one of the 4 vector space axioms, next we can write alpha naught lambda to the power m v plus this v plus v plus this of course is simply alpha m v, and then using another vector space axiom, you of course from the way we are calculating with these things, you understand what I am talking about, which axioms. In fact, that other axiom is alpha plus beta times v is equal to alpha v plus beta v. That thing, it's extended version, which involves possibly more than 2 terms. Using that, we get this. Okay. Now, if you look at this, this is nothing but q of lambda times v. Now, you look at the first one and the last one. On v, we have applied qt and we are getting q of lambda v. So, by theorem 6 to 1, because theorem 6 to 1 works both ways, and v was non-zero previously, now also it's non-zero. So there is such a non-zero vector v for which this equation is true. So by theorem 6 to 1, q of lambda, this scalar, is a characteristic root of this operator q of t. Is a q of t, and that completes the proof. Although the calculation is a little big, but there is no twist in this proof. It's straightforward. Alright, now next we come to that result which I was saying is much more important than this one, and it's going to be called a theorem. This is theorem 6 to 2. Let lambda in F be a characteristic root of t in A of v. Okay. Then lambda is a root of the minimal polynomial of t. That's the claim, but there is a little more also. In particular, t can have only finitely many characteristic roots in F. Alright, so that means any characteristic root is going to be a root of the minimal polynomial of t. Now, how does this claim follow from this? Let us see. Proof. In the beginning itself, we are going to use that vector criterion, that because lambda is a characteristic root of t, so there exists a non-zero v, on which if you apply t, you are going to get lambda times that vector. So by theorem 6 to 1, Vt is equal to lambda v for some non-zero v. Okay, should I now should I apply theorem 6 to 1 here itself, or I think, oh, okay, no, let me just change it. I can do it this way also, but there is a better way. By the previous lemma, by lemma 6 to 1, P of lambda is a characteristic root of P of t, where Px is the minimal polynomial of t over f. Okay, so the previous lemma says that for any polynomial, you evaluate the polynomial at that characteristic root. Whatever field element you are going to get, that is going to be a characteristic root of the polynomial, I mean the operator that you are going to get if you evaluate the polynomial at that operator. In particular, we can do this with the minimal polynomial of t, so that P of lambda is going to be a characteristic root of P of t. Now I am going to use theorem 6 to 1 with this operator and this characteristic root. By theorem 6 to 1, there exists a non-zero vector in V such that Vp of t is equal to P of lambda V. Okay, but we know that P of t is actually the zero operator, because if you evaluate the characteristic polynomial of an operator at that operator, I said characteristic polynomial, minimal polynomial of an operator at that operator, you are going to get 0, because minimal polynomial is the monic polynomial having minimum degree and which also annihilates the operator, that is, it gives us 0 like this. So, and this 0 is what 0? This is the 0 element in the algebra AP, the 0 operator, which sends every vector to the 0 vector. So, if you apply P of t on V, you are going to get the 0 vector in capital V. That is equal to P of lambda V. Now, let us recall not a result but simply an observation from the beginning of our vector space theory. We saw when we were introduced to vector spaces for the first time, there we saw that a scalar multiple of a vector, if it is 0 and the vector is non-zero, then the scalar has to be 0, and here our vector is non-zero. So this implies that P of lambda is equal to 0, and that's how our characteristic root lambda is a root of the minimal polynomial P as well. So lambda is a root of the minimal polynomial Px. Now the minimal polynomial we know is a polynomial of some degree which is a positive integer, and we also know that this polynomial cannot have more than n distinct roots if n is the degree of this polynomial. Okay, and also right now, just now we have proved that each characteristic root is also a root of the minimal polynomial. So because the minimal polynomial has at most finitely many roots, so there are also at most finitely many characteristic roots of t. Since P of x can have at most degree of p of x roots in f counting multiplicities can have at most this many roots in f t can have only finitely many characteristic roots in f. In fact, we know something about the degree of the minimal polynomial from the previous section. This is at most n square, where n is the dimension of V over f. But anyway, there is no need to actually mention this. It's just something we know, and that is the proof. So although the previous lemma was not that interesting in its own right, but it has this very interesting consequence that any characteristic root of a linear operator is also a root of its minimal polynomial, and as a result there are at most finitely many characteristic roots of any operator in the field. Now after this also there are some things that come next in this section, but we are going to do that in another video, the next upload on linear algebra. I mean, essentially we are doing linear algebra. And that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.